In this video, I'd just like to work through several examples using separation of variables. So in all of these, the goal is going to be to come up with the solution to the initial value problem. So first example, if I have dy dx equals e to the x minus y, and y of 0 is 2. So importantly, this is a separable differential equation because we can write this right-hand side as e to the x times e to the minus y. So in my first step of separating the variables, I want to divide both sides by e to the minus y. It's going to be easier to think about that as multiplying by e to the positive y. So this would really be this. If I had written that as 1 over e to the minus y, which is equivalent, it would have been harder to think of the integral there. And we can keep the x's on the right-hand side. So now we want to anti-differentiate both sides. On the left-hand side, we're going to get e to the y. On the right-hand side, we're going to get e to the x, but I'm going to bring in my integration constant. And we want to solve now for y, which will involve us taking the natural log of both sides. So our general solution here is going to be y equals the natural log of e to the x plus c. Now, when I'm now putting in my initial condition, or maybe I'll pause here and point out that we've seen an example where we simplified when we had e to the kx plus c. There's not a similar log property that would allow me to simplify the structure of this, so it's very important that I have that plus c inside of the log function. Now, using the information that y of 0 is 2, I come to my general solution, plug in 0 for x, and what I would get is e to the 0, which is 1. So we'd have natural log of 1 plus c is 2. And our goal is to identify what c is so that we can drop it back in our solution function here. So I've got the expression natural log 1 plus c equals 2. That means that 1 plus c is equal to e raised to the second power. And therefore c is equal to e squared minus 1. That's going to replace c in our general solution. So our specific solution function here is the natural log of e to the x plus the constant e squared minus 1, all inside of the natural log. Second example, if I have dy dx equals the arctangent of x divided by y, and y of 0 is 4. Then separating my variables, I'm going to get 1 over y dy equals arctangent of x dx. And we want to integrate both sides. Now, importantly, this is going to be a chance for us to review some integration techniques. We've dealt already with 1 over y, but dealing with the arctangent of x, let's just remember that the arctangent of x would be a classic case where we could use integration by parts. And in particular, we're going to treat that as u, and in that case we're going to treat dv as essentially 1 dx, which would make v x, and our du now becomes 1 over 1 plus x squared dx. So the right-hand integral is equivalent then to x arctangent of x minus the integral of x over 1 plus x squared. Now, to evaluate this integral, we could use u substitution. I could view u as 1 plus x squared. And in that case, what we would have is 1/2 1 over u, because the derivative would be 2x dx. So I'm thinking over here, u is 1 plus x squared. du is 2x dx, so importantly 1/2 du would replace x dx. All of that is just to help me identify then that the integral of arctangent of x includes x arctangent of x, which we got from our integration by parts. And then further evaluating that second integral, I can use u substitution. We would have the integral of 1/2 times 1 over u, which would be 1/2 natural log of u, where u is 1 plus x squared in absolute value. And we would put this additive constant here. So what that means is, in my bigger question here of separation of variables, the integral of 1 over y is going to give us, that should actually be the integral of just y. So 1 over y in the original expression, I multiplied y over there. So the integral of y is going to be y squared over 2. And now we're equating that to the integral of arctangent of x, which required a little extra work, which we did above. And so we get this on the right-hand side. I can drop the absolute value bars because 1 plus x squared is always positive, but of course it's not wrong to keep those. And now I can multiply both sides by 2, telling me that y squared is 2x arctan x minus natural log of 1 plus x squared plus c. Again, to be clear, you could write this as plus 2c. I'm just representing that as some additive constant. I'm absorbing that 2 in there. Regardless, we should get the same answer after we plug in the initial condition. So 2c would be perfectly acceptable there as well. And then finally, we take the square root, and we're going to get here that y is equal to plus or minus the square root of 2x arctangent of x minus natural log of 1 plus x squared plus c. Now, one thing to consider here is we're going to be able, after plugging in our initial condition, to further refine the plus or minus. We know that y of 0 here is 4, which is of course positive. So that means that we're going to choose the positive square root. If I had an initial condition that was in fact a negative number, I could have chosen the negative square root. So in my final answer, not only am I going to evaluate c, I'm also going to write that it's simply the positive square root. So now to find the value of c, knowing that y of 0 is 4, we're going to be able to say that when I plug in 0 for x, notice that we're going to get the square root of 0 minus the natural log of 1, which is 0. So we're going to get square root of c. And we're saying that the square root of c is 4. So if we square both sides, we're going to get that c has to be 16. So our final answer is the positive square root of 2x arctangent of x minus natural log of 1 plus x squared plus 16. If you had left that additive constant as 2c, then you should have found that 2c is 16, so we would have ended up at the same place here. Okay, another example. If I have dy dx equals y times x plus 2 over x minus 3, and suppose y of 4 is equal to 2e. Then again, this is a product of a function of y and a function of x. We can separate our variables, and that's going to leave us with 1 over y dy equals the not integral yet, but x plus 2 over x minus 3 dx. And now we could integrate both sides. Just like the last one, I would say the harder integral here is the x plus 2 over x minus 3. So I would pause and work on that one. So when I have this integral, the difficulty is the fact that we can't really break up that denominator. However, we could let u equal x minus 3. Then the nice thing about that is du is dx. So in terms of rewriting this, the bottom becomes u. We've got du here. But remember, we've also seen then, I don't want to write x plus 2 in the top, but this can be rewritten to say that u plus 3 is equal to x. So we can really rewrite the numerator to reflect that. And in particular, what we're going to get is, this is u plus 5 over u. Now I can split that as the integral of 1 plus 5 over u, taking the numerator and splitting that fraction apart. And we can anti-differentiate that to get u plus 5 natural log u plus c. And rewriting my final answer in terms of x, this would leave me with x minus 3 plus 5 natural log of x minus 3 plus c. Now, this is perfectly fine. I'll also point out that some people would take the minus 3 and the c and combine those to just write that as plus c. Either way is fine, and I'll just keep it as it is here. So now that we've done that work, now I can come back to the question at hand. The antiderivative of 1 over y is the natural log of absolute value of y. And it's equal to what we just calculated. X minus 3 plus 5 natural log of x minus 3 in absolute value plus our additive constant c. We would like to solve for y here. So what we can do is raise e to both sides. And that's going to leave me with e to the right-hand side. Now, we can split that up in a number of ways. That's going to be e to the x minus 3 times e to the 5 natural log of x minus 3 times e to the c. We can simplify several things in here. So for one, I'm going to write this as c. That we saw before. So I'm going to have a c multiplier. I have e to the x minus 3. But we can also rewrite this. That's the same thing if you think of our log properties. That multiplier of 5 could be brought inside so that it's now e to the natural log of x minus 3 raised to the power of 5. And the reason that this is preferable is that this now simplifies to just x minus 3 raised to the 5th power. And what we'll see then is that that comes in here after simplifying that. So that's the advantage to trying to simplify this as much as possible. That is, of course, much more familiar than what I've circled in pink. The other question that you might have or might have had earlier is you'll note that I dropped the absolute value here. It's not that it's gone, but instead, the absolute value we're going to think about bringing in potentially dealing with some kind of sign. But because we can always choose our multiplier here from the initial condition, that positive or negative in some sense will be accomplished with that. So now I have my general structure, and the last thing to do is to plug in the point that we know the solution passes through. So we're given that y of 4 is 2e. So I come back up to my general equation here and plug in 4 for x. In doing that, I get e to the 4 minus 3, and we have 4 minus 3 to the 5th power. We want that to equal 2e, but notice that that simplifies to c e times 1 to the 5th. So this is really telling me that the value of c is going to be 2. So what we have here is that my final solution is going to be y equals 2e to the x minus 3 times the quantity x minus 3 to the power of 5. And one last example. Suppose we're given f prime of x equals 2f of x over x, and f of 2 is 16. What I'd like to point out here is that while this notation is different, this is really identical to the form of what we've seen above, in that you could rewrite this as the following. So think of f of x as y in this case. So this is the same thing as saying dy dx equals 2y over x. Y of 2 is 16. So we can always interpret it that way. And so I can still go about this in much the same way we did before. I have a separable differential equation. Separating the y's, we're going to have 1 over y dy equals 2 over x dx. That 2 can stay where it is, or I could have brought it down into the denominator with y. Either is fine. So anti-differentiating both sides, I'm going to get the natural log of the absolute value of y is equal to twice the natural log of the absolute value of x plus c. Now, much like we just observed in the last part, I can tell that I'm going to be heading towards exponentiating both sides. So I would like to rewrite this as the natural log of x squared using my log properties. Then when I raise e to both sides, I'm going to get y equals e to the natural log of x squared plus c. We know we can bring that e to the c out as just a constant multiplier. And likewise, if I take e to the natural log of x squared, that's going to give me x squared. So it turns out that we get a power function, which would have been hard to notice if we hadn't simplified. Finally, knowing that y of 0 should be 16, I can plug in, that's y of 2, not 0. So plugging in 2 to my general function, we get that says 4c should be 16. So c would be 4. And so my final answer, you could either express it as y is equal to 4x squared, or f of x is 4x squared if we want to use the original notation. Either is fine. So we've gone through several examples and seen how this is very powerful. We're able to solve these differential equations where it's not the case that I could intuit a solution. However, I do want to point out that this only works, of course, if we have a separable differential equation. And all of these examples that we went through are separable. This does not help us at all with the tons of differential equations that are not separable. And that's why there's a whole course devoted to that, because there are lots of other techniques that we can use in lots of different situations. So this only does apply to a very small corner of this group of all differential equations.